Okay, thank you for passing this up. Thanks. Okay, so on your lab sheet side, do you have BCl3 or you have boron trichloride, BCl3. Let's draw that one real fast because I want to make sure you're understanding about a couple of these structures have actually less than octet, and some of them have more than octet. So octet is a guideline. It's a rule, but it's a guideline because you'll actually find quite a few of them that disobey octet. So what's the very first step when you're drawing a Lewis dot model? Count the electrons. What is BCl3, which is on your lab sheet. So I'm doing one of them for you, okay? What does boron carry? 3 plus 3 times each of the chlorines at 7, so that gives us 24 electrons. Okay, so boron is tiny. It's just a little bit bigger than beryllium. So hydrogen, beryllium, and boron are all going to possibly not mean octet, and that's okay. So who's definitely going to be in the middle? Boron, and then you're going to separate your chlorines in 3 different directions, and then you're going to octet them up here. Okay, so give everybody octet, so that's 8, 16, 24. Okay, who does not have octet? Boron. Okay, so what some of you guys are going to do is you're going to be like, oh, how about I just make them share? And so you'll put a double bond here instead of all single bonds. And that's okay. It's not 100% correct, though, because chlorine is chlorine's way up here, so it's really what? What's the trend we're looking for, huh? Electronegative, right? It's very electronegative, and so it tends not to really want to overshare. It tends to want to have more electrons than give. So chlorine, it could give that double bond. I mean, that lone pair to make it a double bond, but that's like not really cool with its trend. It likes it likes electrons more than boron does. So boron's like, all right, dude, you can have them. I'll stick with 6 electrons around me, and chlorine keeps all of its lone pair. So that's probably going to be your best drawing for that. What shape would that be? Trigonal. Is it a pyramid or is it flat? It's flat because there are no lone pairs on boron. No lone pairs means there's no pushing or pulling, so there's no pyramidal structure. It's a flat structure. So what's the word for flat? Planar. Okay. So it's going to be trigonal planar. Is this one going to be polar or non-polar based on the distribution of the electrons around it? Non-polar, because the dipole moments are probably pointing equally in strength and direction away from boron. So if it's like negative, 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 that's going to be non-polar. Okay, so now we're going to build onto this. And today we're going to talk about like what kind of interactions do 2 non-polar molecules do together and what do 2 polar molecules do together. And that'll kind of be our conclusion for the geometry stuff. Last one, the xenon, oxygen, and fluorine. I think there were 4 of them. Can you double check that for me? 4 of them. Okay. So these are the 2 that I was going to do from last week. Tell me your count here. Xenon carries 8 plus oxygens 6 plus 4 times 7 for fluorine. So that's 28, 34, 40. No, 42. Thank you. Okay, so who do you think, I mean, I know we have options here, but who do you think is going to be the middle? So what's our order of operations here? We said carbon for sure, but we don't have a carbon. So then we went to singleton, but we have 2 singletons. We have a xenon that's a single and an oxygen that's a single. And then the biggest. Good job, guys. Biggest. So who's bigger, oxygen or xenon? Who's bigger? Xenon, definitely. Xenon's farther down the periodic table, oxygen's farther up. So xenon's going to be in the middle, and then everybody else just gets straight up attached to the central atom. Don't put like a train of them. Okay, they're all attached to the central. Oxygen, fluorine, 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 fluorine. Okay, so then now what we have to do is double check octet, right? So give everybody octet by double bond, lone pairs everywhere. And then let's check. How many electrons are on my structure thus far? How many, Abby? 40, right? So we've got 8, 16, 24, 32, 40. So what do I do with those last two? I put them where? On xenon. Remember, if you have extras, you have to put them as a lone pair on the central atom. If you're scared they're going to get lost in the mix here, circle them so they're very clear that they are on the central atom. So that's going to be what your xenon, oxygen, and fluorine structure looks like. So this one's shape is going to be a little different. You won't find it on your sheet. I want you to build it and then so you can figure out the shape from there. Okay? So hold off on that one for shape and clarity. Okay, let's jump into IMFs. Okay, so here is a, let me go to the first slide first, and then I'm going to pass out some papers because like this stuff, this is what we're going to take notes on today after I pass this out. Go ahead and write down this stuff right here first. And this stuff is for tomorrow, but I'm going to give it to you today because I won't see you tomorrow, and you know, sometimes when I'm not here, stuff doesn't happen when I want it to, so I'm going to give it to you now. So write down some stuff here first, a little intro, and then we're going to actually talk about the 3 big topics. And y'all's free responses were baller. Let me say, they were really good. Significantly higher than my first response. Just saying. If some people really work a little bit more, kind of get the family together and practice together. And while I'm thinking about it, Tuesday, ACT, we don't have till tomorrow, okay? No till tomorrow. Long last half the day for you. Have to make yourselves. Thursday, I have a conference I have to attend in Raleigh, so I won't be here, but my AP kids will be here to tutor you. Just have somebody adopt you, okay? And then Friday, I'll do an honors chem unit 2 review test. So I'll tell you if you're required to come to that or not. Okay, so 2 big ideas: intermolecular forces, intramolecular forces. I'm going to start with the ones that we're very, very familiar with. Those are the intramolecular forces. Remember, intra means within. So, like, if you're an introvert, it means you like to, hang out with yourself. You don't necessarily like to talk to other people. You're very good with kind of what's happening within your own mind and self. So, 2 different examples of intramolecular forces would be things like ionic bonding and covalent bonding. So those are 2 different bonds that we've talked about extensively. So what we have to deal with now is sometimes we're going to have a covalent molecule interacting with another covalent molecule with another one, with another one, with another one. And so they interact with really, really strong forces between them or really weak forces between them. And we actually have names for those forces of attraction. They're called, the kind of umbrella term is intermolecular forces, which I'm not going to say that or write it out like that anymore. I'm going to say IMFs, intermolecular forces. They come in 3 varieties: hydrogen bonding, dipole-dipole, and I wrote this down last week with reading guide 8, I remember, and London dispersion forces. And I have these all on the next slide too. So we're going to review those 2, HB, DD, and LDFs. So those are the forces we're really talking about. What happens is sometimes we're going to have to talk about how these covalent molecules interact with each other. So for example, if I have a water molecule next to another water molecule, how do they interact? Well, we know they stick together, right? What's the word for 2 water molecules sticking together? Starts with a C. Cohesion. What's the word that talks about water sticking to like the sides of a glass? Adhesion, right? So we actually know what these things are. We know water has really good surface tension. They stick together. Well, what the heck is causing water to stick to other waters? Anybody? What's this force of attraction between them? It's the same thing that holds DNA together. Hydrogen bonding. That's it. And you hear the word bonding there. That dashed line means it's not a bond. It means it's an attraction. I hate the word bond because sometimes bond means bond. Sometimes it doesn't mean bond. Like, why can't we just say bond and attraction? Chemist? I don't know. So they've messed up there. It's not an actual bond. It's an attraction. So that's one that you're actually somewhat familiar with because you know what DNA, you know it has to unzip, right? If not, we're never going to replicate our DNA. So it has to be weak enough to pull it apart, but strong enough to hold it together. So it doesn't just fall apart and then, we're smushed. Okay, so here's our video first. Actually, let me go, I'll come back to this part. This is our DNA. So like I said, what's the dash line mean? Attraction, but that's called a hydrogen bond. We can call it a hydrogen attraction if you want to, but hydrogen bond means the same thing as hydrogen attraction. Okay, this is what we're going to take notes on first. I want you to see these attractions first, and then we are going to actually draw them. I talk about them in context on like why they're actually important. So, I already passed these out. Yay. Okay, I was like, what? I never had these. So I want you to try to explain, draw, and do what you can on the chart as this guy explains it. He's a little goofy, but who's not, right? Who's not? Oh, no, we're not ready, mister. Let's make sure the music's off. Is it off? Pandora's having problems. That's okay. Okay.
The forces in between molecules. In particular, we're talking about the attractive forces. The attractive forces between molecules is really what ends up governing all physical properties. And when I say physical properties, I mean boiling point, melting point, viscosity, surface tension.
This is the only reason we were talking about intermolecular forces, because it makes everything else make sense. It makes, why is this boiling point high? Why is this low? We now have a reason about why these are higher or lower. So it governs physical properties. That's one of the most important things probably right now. Governs physical properties.
Stuff like that are physical properties, and it's really governed by how strongly these molecules are stuck together. Turns out a lot of these intermolecular forces also affect the way chemicals react, because a lot of these same forces govern the way chemicals come together, and then if you can get them together, you have the possibility of a chemical reaction. We generally cover three basic intermolecular forces that we give three distinct names. The differences are really pretty subtle. It all comes down to the difference of a positive charge and a negative charge. That's really what the attractive force is about. So you have positive and you have negative. The more positive it is, the more negative it is, the stronger the force. This is simply Coulombic attraction. Positive attracts negative. And we have all degrees of this. It's just a matter of how positive and how negative. Most molecules, being neutral species, do not have full positives and full negatives on them. That tends to be the world of ionic molecules. So we're constantly writing partial positive and partial negative. We even have the way we symbolize it on paper.
Remember those? Partial negative, partial positive. We've been saying that. We've been kind of thinking like this side of the water molecule is partially positive, this side is partially negative, and we've been saying it. Make sure you're comfortable with like looking at it. It's like a lazy 8. You didn't quite finish the 8.
Be used to as these partial positive and partial negative charges. Matter of fact, if you can get enough distribution within your molecule to where you have a lot of positive charge on one side and negative charge on the other, you can get what we call a polar molecule. A permanent dipole is a polar molecule. And if you have a permanent dipole, you're going to have a setup within the molecule where you always have partial positive, always have partial negative. And those are going to get together. That's called dipole-dipole interaction, and that is the strongest interaction you can have within a molecule to another molecule. Now, we have a subset of that that's actually the strongest version of it. They're even stronger than a regular dipole-dipole. And we call it...
Okay, so what he said was dipole-dipole was strongest. What he meant was polar molecules undergo dipole-dipole forces. Non-polar molecules undergo a different type called London dispersion forces. But there's that subset that he's talking about right now. That's actually the strongest of the dipole-dipoles. And that's hydrogen bonding. So basically, if you're writing down strength and descriptions, hydrogen bonding is the strongest of all intermolecular forces. Hydrogen bonding. So I hate that he actually said the dipole-dipole, and then he's like, a subset of it is hydrogen bonding. But he's saying right now, hydrogen bond is the strongest of all intermolecular forces. Dipole-dipole forces is the next strongest. And London dispersion forces are the weakest. So the way I've got them ordered on your paper is weakest to strongest. And he gave you a little drawing on the dipole-dipole if you want to give yourself a quick sketch. It's right here. And so basically, the real deal here is that this molecule on the left has a partial positive and a partial negative. What part of this molecule is attracted to the other molecule? Well, you should be able to tell there's opposites attracting. So another molecule on the right also has a partial positive, partial negative. That's just indicative of the fact that they are polar molecules on equal distribution. One side is positive, one side is negative. And so what's attracting in the middle? Right, the partial positive and partial negative of two different molecules are attracting. And that's what he termed also earlier Coulombic attraction, positive negative attraction. So it's between two molecules. So anytime you draw it, you have to have at least two molecules depicted. If not, you're drawing an intramolecular, not an intermolecular.
Stronger than a regular dipole-dipole. And we call it hydrogen bonding. And it's really because it involves hydrogen being the partial positive part of this molecule. Anytime hydrogen is covalently bound to a very electronegative element, and I'll be specific here, it has to be bound to fluorine, oxygen, or nitrogen.
Okay, so you have to memorize the elements that are involved in hydrogen bonding. It's only when you have a hydrogen bound to F, O, or N. So I like to say hydrogen bonds are fun, guys. They're super fun. Fun, not fun. Okay, so that's the partial positive, which is the hydrogen side, because it's got low electronegativity. And oxygen, fluorine, and nitrogen are all way, way, way up on the upper corner. So what do you say about their electronegativity? It's very high. So it's this distinct factor of a very large difference in electronegativity that makes these hydrogen bonds so different than just generic dipole-dipole.
It is. It becomes so partial positive, and the oxygen or nitrogen or fluorine becomes so partial negative that you get an even higher amount of attraction. So we go ahead and classify that in its own class. We call it hydrogen bonding, but it's really just dipole-dipole interaction, just up a notch. At the low end of the scale are nonpolar molecules. Now, nonpolar molecules are molecules that have no dipole moment whatsoever. They usually are nonpolar due to symmetry arguments, meaning that whatever you argue pointing one way, there's the opposite way covered somewhere else on the molecule. So all the symmetry wipes out the polarity of the molecule. Good example of this is carbon tetrachloride. Carbon tetrachloride has 4 very polar carbon-chlorine bonds, but they all nullify each other as far as distribution of charge. So it's a nonpolar molecule. However, it will attract another carbon tetrachloride molecule. They do stick. It is a liquid. So there's definitely forces there. So what are they? They're dispersion forces, and they are based on what we say are temporary dipole moments. Temporary dipole moments is when the electrons within the whole molecule are in such flux that at any one point in time, you're going to catch it.
Okay, so he said temporary dipole, because these electrons are moving. They're really, really high vibrancy kind of deal, right? So we know this is nonpolar. There's no partial negative, no partial positive, like we have in the polar molecules, because there's an equal distribution of charge all the way around. Well, for a nanosecond, for a picosecond, for something really tiny, one of these electrons, like say, for example, like just maybe this is fluorine and fluorine or something, the electron accidentally scooches to the other side. So immediately we have an instantaneous point where there's 5 electrons on that side and 3 on this side. So that right side has a really, really tiny partial negative, and this side has a really, really tiny partial positive. But it's only there for an instant, and then it comes back to its normal place. That's why it's called temporary, because it's not there for long, and that's why they're so weak, because it's not a permanent dipole. It's not a permanent state of a negative and positive. That's going to cause some attraction.
With a slight positive end and a slight negative. And another molecule is going to get caught in that same time, and there's going to be an attraction there. This will change over time and time again in very fast time frame, yet the attraction is there. So it's a very slight attraction. It's not nearly as strong as a permanent dipole, But that's what we call dispersion forces. So that's all three forces together there. We've got hydrogen bonding up at the top, right under it, dipole-dipole interaction, and a little bit below that, we've got dispersion forces. Those are the three major intermolecular forces at play with all molecular substances.
Okay, thanks, Paul. Let's go back here. So tell me some things you wrote down here. Which definitely is the strongest? Hydrogen bond. Okay, so strongest. And then what were the important elements involved? So hydrogen bonded to fluorine, oxygen, or nitrogen. Okay, this one's the second strongest. Okay, what was one of the important parts here? Okay, so there's a molecule with a partial positive and a partial negative attracted to another one with a partial positive and a partial negative. So basically you're telling me these molecules are polar or non-polar? Polar, right? So this one's polar molecules. This one's polar molecules as well, but a special case one because it has to have this included in the molecule, H bonded to FO or M. These are present between what kind of molecules?
Non-polar.
Non-polar molecules. And this one's definitely the weakest. And it's a temporary situation where you have a temporary partial positive and partial negative. And what was causing this partial negative, partial positive? What was moving? Electrons. This is a multiple choice question. Most people get wrong because they forget it. So I've seen this 5 years in a row. Electron motion or unequal, not unequal. I'm trying to think of the word I used in the multiple choice question. How about I just say electron dispersion? Electrons disperse themselves unequally. They're moving around for just a moment, and that causes that difference in charge. And that causes that temporary attraction. So this one, strongest, second strongest, weakest. Differences are polar versus non-polar versus polar molecules. There's a little bit more to help us order them. So these are all important because of what big idea? This controls what about molecules? Their physical properties, right? Melting point, boiling point, those things are probably the more important ones, and also solubility, meaning who's going to dissolve in water, who's not going to dissolve in water, for example. So I have some more details, and this is you can add to the chart, add separately. I don't care. These are the things that I wanted to add. The only things that I think are different is merely the fact that intermolecular forces have another name, like everything does, right? Van der Waals forces. Guess who came up with this, guys? Van der Waals. You guys are smart cookies. So the one fact about London dispersion forces is that as you increase the number of electrons, then the strength of that London dispersion force, or dispersion forces as he called them, increases. So basically more electrons increases London dispersion forces. So that's going to help us because we can compare now two different molecules with London dispersion forces and we're like, hey, this one's got a higher boiling point than this one because its forces are stronger than this one. I have a ranking chart underneath your notes. We're going to get to that in a second. Dipole-dipole, the only thing was not in the video is if you had to compare two molecules with dipole-dipoles, you're like, who's got the stronger dipole-dipole attraction? It's going to include the increasing molar mass. This simply means sum of masses of the elements, or of the atoms. And I'll do an example of that in a second too. So the fun fact at the bottom is just going to help you compare to the same types of forces so you can figure out who possibly has the higher boiling point or lower boiling point. Lastly, we have the hydrogen bonding, like we've stated before, and so they also increase, the forces of hydrogen bonding attraction also increase with increasing molar mass, or masses of the atoms collectively. So one thing to note is that anytime we say the word molecule or molecular, we're saying something is covalently bonded. So we talked last week about, covalent bonds, they're strong. A covalent molecule attracted to other covalent molecule, those are what we're talking about right now, intermolecular forces. Last week we spoke of this thing called lattice energy or charge product. That was with an ionic compound. So we're going to talk about that compared to covalent molecules now. Because essentially, if I give you, I don't know, 15 different things, ionic covalent molecules and all that together, and I want you to rank them from highest boiling point to lowest boiling point, we should be comfortable with that. So we noted last week that ionic bonds, can I go to the next page? Cool? Yes? Shake your heads. Thank you. Okay. So, I'll come, this is my pretty picture. This is basically what we're talking about before I say what I was going to say. What are these little dashed lines again? Attractions. And if I'm talking the weakest intermolecular force, London dispersion. All of these are London dispersion forces, keeping fluorine attracted to fluorine and chlorine attracted to chlorine, and so forth. I'll talk about the differences in their sizes in a second. Let's rank these. This is just pictures of hydrogen bonding. This is your ranking system. Okay? What you see is the highest of all the relative strengths. Ionic. So ionic bonds are the strongest, meaning they have the highest boiling point, or melting point, or whatever point we're talking about. And if you had to compare to ionics, what's going to help you figure out who has the stronger attraction for each other? We did an example of this last week. Do you remember the charge product where we looked at like the charges of, let's say, sodium chloride versus sodium oxide? What's the charge of the sodium? Look at your PTOE. Tell me how many valence electrons sodium has. Can I get some volunteers here? How many valence electrons does sodium have? One. So what's its charge? Well, it loses an electron, so positive 1. Okay, so sodium has a positive 1. Chlorine has how many valence electrons? 7. So what will its charge be once it gains or loses electrons? -1, because it loses because it gains an electron. So what's the charge product? It's just 1. Because I told you guys we had to do absolute value, because the charge in the actual sign doesn't matter. It's 1 times 1, which is 1. Okay, what is sodium's charge again? 1 plus 1, right? What's oxygen's charge? It's got 6 valence electrons. But what's its charge? -2, because it has to go forward 2 spaces to attain octet. So what's 1 times a 2? 2. So who has the stronger charge attraction? This guy. This is called sodium oxide. So what we would say is sodium oxide, which we're going to go over tomorrow, okay, nomenclature, it has a greater boiling point than sodium chloride because its charge product is bigger than the other one. So that's how you compare ionic to ionic. You'll have a couple of times where you have to compare ionic to ionic, but sometimes you just have to compare ionic to covalent. So what you have to deal with here is these two are going to be polar molecules. And so if you're going to compare the hydrogen bonding to something else that's hydrogen bonding, what's going to help you? Would you just write down that helped you figure out who had the higher boiling point, for example? Molar mass. You write down the higher molar mass would be the higher boiling point. Same thing for dipole-dipole. Look at its molar masses. Whoever's higher in that little subgroup will help you determine that. And then for London dispersion, what helped you determine for a nonpolar molecule, which would have a stronger London dispersion force? You just write this down too. A number of electrons, right? So this one's number of electrons. These over here are molar masses. And I'm going to do a big chart with you to help kind of bring this to life, because you need examples probably for this more than me just talking. So guys, we're going to draw structures first, then we're going to talk about the polarity, then we're going to order them. So this is going to be quick and easy before I start some other stuff, because I'm expecting you can do a Lewis dot model in a jiffy, okay? So count the valence electrons for ammonia. Count them up. How many total? You need your periodic table out. Go for it.
8.
8. Who goes in the middle? Nitrogen, and then hydrogen, hydrogen, hydrogen. We've drawn this one about 3 times now. Lone pair on top. Okay. Is that polar or non-polar? So before you can determine the molecular polarity, you have to consider the shape and the bond polarity. So in your head, you're going, okay, this shape is what? Do you guys have your little sheets? I might not have passed them out. Okay. What shape is that? Shout it out.
Trigonal.
Here's trigonal what? You see that lone pair on top? Probably pyramidal, because that lone pair is going to be pushing down, creating a pyramid structure. Here's a couple more. That's the right. Here's what the shares are. Basically, you need to back side. That's it. Okay, so that one's trigonal pyramidal. If it's a trigonal pyramid, is that going to be polar or non-polar? Okay. Does everybody have a little sheet they can work from to share? Yeah. Okay. With me. It's a triangle pyramid. There's a lone pair on top. It's partially negative up top. It's partially positive on bottom. Polar or non-polar?
Polar.
Polar. Okay. What are our 2 options for the IMFs for polar molecules? Dipole. So is Matt the only one up here? Okay, let's go. Evan. Okay, you're next on my list. What are the only 2 IMFs present for polar non-polar? For polar molecules? Okay, which one applies here? Why? Right, hydrogen bonded to a nitrogen. So that's what the only reason it applies. Okay, we're writing down across. We're going to do comparative boiling point at the very end. Let's do water. How many valence electrons? How many? There's hydrogen has how many? How many does hydrogen have? 1. Okay, my laser. Okay, hydrogen is in group 1, has 1 valence electron. Oxygen has 6. So that's a total of 8 valence electrons. Okay, so 8 valence electrons. Who goes in the middle? Oxygen, and then hydrogen, hydrogen. Equally, symmetrical. And then who needs octet? Oxygen. And I'm going to put 1 here and 1 here. Niall, look on your sheet. Tell me what the shape of that is.
That would be a
2 lone pairs, 2 ligands. Right, that is bent. If you're bent and you have the lone pairs up top and the 2 hydrogens down low, Melanie, is that polar or non-polar? Right, because you can see there, when it bends, it kind of creates a shape like this, where you have partially negatives up top and the 2 hydrogens are down low. They're partially positive. So there's a difference in polarity or distribution, so it's polar. Okay, Nicole, would you say that's hydrogen bonding or dipole-dipole? Because there's a H bonded to an O, right? So hydrogen bonding is a special type. Okay, cool. Next, carbon tetrafluoride. Count your valence electrons. So total, Abby, total? 32. Okay, so 32 valence electrons, carbons in the middle, fluorine, 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 fluorine. And then, so you guys, I think, are good with the central and then distributing your other atoms. Everybody needs octet, though, so then you double or you give them all lone pairs. So I think I've got 32 there. Is that right? 8, 16, 24, 32? All right, Lindsay, what's the shape? Tetrahedral. So it's like one's up, one's to the side, one's back, and then the other leg is the other one. Fluorine, 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 fluorine. Emily, do you think that is equally distributed or unequally distributed? Equally distributed. So if it's a big equal distribution, Maddie, is that polar or non-polar? Right, non-polar. So Jasmine, is that going to be, what IMF would that be? So look back at your categories. London dispersion forces, because that's the only one that applies to non-polar molecules. Great, you guys are doing fantastic. What kind of molecule, or what kind of thing is this, Trinity? Is this covalent or ionic? It's the next one. Yeah. Magnesium is a metal. Chlorine is a nonmetal. How do we draw those? Those don't look the same as these.
You have to like draw with the arrow, like it becomes magnesium.
Okay, so I'm just going to kind of do that, and you tell me how many electrons magnesium has. Valence electrons. 2, because it's in group 2. Okay, Scott, tell me chlorine. 7. 1, 2, 3, 4, 5, 6, 7. You see that I have 2 in the formula for chlorine, so I actually need a second chlorine. So I'm going to draw it kind of higher. I'm running out of space. I hope that you guys are fitting them in your boxes. Okay, so then I know that, so Trinity said you're going to have to draw the electrons actually transferring. So I'm going to just draw these guys going to the chlorines. And so that leaves magnesium with a 2+ charge because it lost 2 electrons. And each chlorine gets a charge of what? What's up, Allison? Each chlorine gets a -1. So there's one's going to go to this chlorine, and one's going to go to this chlorine. So that extra electron leaves it with a -1 charge. And that's where we put our electron dots in brackets. And I'm just going to put the 2 on the outside like that to say there's 2 of these guys that look exactly the same. Okay, so does it have a polarity? No, because it's not a molecule. Does it have a shape? No, because it's not a molecule. Does it have an IMF? Intermolecular forces? No, because it's not a molecule. So I'm just going to put the word ionic here to remind me that I have to think about the actual chemical nature of it. Okay, got 3 more? Okay, so phosphorus trichloride. Peyton, tell me the number of electrons. So phosphorus had 5 plus the line of 5, okay. So plus 21. Okay, so 26 total electrons. P in the middle, 3 chlorines to the side. Octet on everybody. This should, like, you should be dreaming about those structures. We've drawn them so often now. Hopefully good dreams, no nightmares. Okay, so are there 26 there? Okay, so you'll notice there's only 24. So we're up at the others. Lone pair on phosphorus, right? Because phosphorus didn't have octet. So you had to give it octet, and that's where the lone pair came in to help there. Okay, Allie, shape. So trigonal pyramid. All right, so we've got this nice shape with the phosphorus in the middle, lone pair on top, 3 chlorine legs below. Chase, would you consider that a polar molecule, polar being unequal distribution or nonpolar equal distribution?
Non-polar.
So hold on, think about it again. You have to like visualize. Okay, so phosphorus at the top, lone pair. So there's actually like this, like that. Phosphorus at the top, lone pair up here, and then chlorine, chlorine, chlorine. Right. There's actually I'm covering up the magnesium chloride now. There's a large negative area up top. There are some negative areas down here, but I would say the lone pair kind of trumps everything else because that lone pair on top is going to really cause quite a negative charge. So we're going to go with polar, and then Avery, is that going to be, so polar is going to be a dipole or hydrogen bonding to work with? Which one? Dipole. So that's dipole. Dunkin' Donuts. Okay. Oh, I love that. They're so close now. Okay, Morgan, how many electrons on nitrogen? So 5 each, right? So total on this N2. 10 electrons. So I think we've drawn this one in the lab, though. What's it look like? You drew this on your lab sheet. It's probably like the second and last one. Triple bond, right? So you had to kind of go through some trial and error there. But there's a triple bond there because there's only 10 electrons total. Allison, is that going to be polar or non-polar? So tell me where the, no, sorry. I know you really have to like talk to yourself. Okay, equal distribution, no sides different, so non-polar. Okay, that's non-polar. James, would that be, what IMF would that be? London dispersion forces. Last but not least, we have sodium chloride. What kind of compound is this, Scott? ionic. So we draw it like we did with the magnesium chloride, right? So sodium has 1 dot. Oh, sorry. How did you know that was ionic? Right. So we have a metal and a non-metal combination. Good. So sodium has 1 dot. Eli, how many dots does chlorine have for its valence count? So valence number of chlorine is what I'm asking for. 7 because it's in group 7. So the group number is the valence number. Good. And then we're going to draw that sodium donating its electron to chlorine. So that sodium has a 1 plus charge and chlorine has octet. Sorry, my dots are everywhere, but you guys know there's octet there. And we're just going to write the word ionic here so we remember the situation here. Okay, well now we're finally to the boiling point part, guys. So we just went through drawing, shape, polarity, IMF. So, Madeline, who's the top boiling point based on the categories that we described earlier for our notes? So you said magnesium chloride. So you just, first of all, you said, okay, let's narrow it down to the 2 ionics. And then how did you choose magnesium chloride over sodium chloride? Right, the charge product. So magnesium's charge, can you tell that it has a 2 plus charge? We actually wrote it here. And chlorine is a -1. So that charge product, mine's a little messy here. So I'm actually going to get some space by erasing this. I need this space. Okay, so magnesium has a 2 plus and a -1. That gives us a charge product of 2. And then sodium chloride is a +1 and a -1 that gives us a charge product of 1. So she said magnesium chloride is the #1 boiling point. It's the highest. So then who's number 2? The other ionic, right? We kind of narrowed it down. Okay, so ionics have been taken care of. Who's next on our list of boiling point? Hydrogen bonding, okay? So Brandon, we have how many hydrogen bondings here? 2. How do we narrow down to who's the higher? Molar mass. Okay, so you guys have your periodic tables out. Let me show you what this is. Nitrogen weighs 14. Do you see it underneath the elemental symbol? Okay, so 14 plus approximately 3 times 1.008 for hydrogen's mass. So that's like a total of about what? So 14 plus 3, 17. Okay, we call that 17 grams per mole. If you want the units now, we're really going to hit those later, but grams per mole is how we describe it. Okay, so we're comparing ammonia, which is hydrogen bonding, to water, which is hydrogen bonding. Look at the masses on the periodic table and tell me what the mass approximately of water is. So 16 for oxygen plus 2 for the hydrogen, so that's about 18 grams per mole. Is everybody seeing where we're getting those numbers? Yes? Okay, so who's the higher one? Water's number 3 because it has a higher molar mass. 18 is bigger than 17. So then who's number 4? The other one. Great, okay. Great. So thanks, Brandon. Who's next, Alina, in terms of the category? Then we'll narrow it down from there. So we did ionic, then hydrogen bonding, then dipole-dipole. How many had dipole-dipole?
Just 1.
Just 1. So good job, Alina. Who's the next one? Oh, hold on, sorry. Number 5 is the phosphorus trichloride. Okay, then you're right. Then London dispersion. So we had a couple of those. We have the one with the nitrogens, and then the chloride. Is that it? Is that it? Okay. So how do we determine from there, Lena, who's higher? By mass? Those are the dipole-dipole and the hydrogen bond. Chase, help her out. Number of electrons. So comparatively, you can see, and I'm going to say look at the Lewis dots for now. Nitrogen has how many electrons that are free around it? Like lone pairs. 2 here and 2 here. So it looks like there's about 4 here, right? Look at this guy. Like, what is that? 6, yeah, 24. So who's definitely going to be higher? Yeah, C4 definitely has more electrons to work with. You can see collectively there's a lot. Even if you counted them up from like the actual electrons assigned to the element based on its atomic number, you would still see the same thing. So this one's going to be the next highest, which is number 6, and then the lowest boiling point is coral nitrogen. Okay, who's ever heard of liquid nitrogen? Okay, what's nitrogen normally? I mean, because we all know liquid nitrogen is a special case. It's like a surprise at your birthday party, right? If you have like a scientist-themed birthday party, which we all have, right? You were shafted as a child. Okay, so it's a special case, liquid nitrogen, because what does nitrogen normally exist as? A gas. Has anybody ever seen solid nitrogen? Me neither. Okay, because it's really difficult to make it go to solid state because its boiling point is so low. It boils at like negative, 100 degrees Celsius. It boils at negative 100 degrees Celsius. So most of the time you're not going to see it in liquid state, never probably in solid state, most of the time in gaseous state because it's already boiled by the time we've seen it. That's why these states of matter make sense because this guy is definitely a gas at room temperature. Who's definitely a solid at room temperature because its boiling point is really, really high? Magnesium chloride and sodium chloride. Those are ionics, right? They're solid. I've never seen gaseous sodium. So I've never seen gaseous salt, right? That would be very cool. That actually might hurt. It'll like hit you. It would ionize your face, scar you. Okay, so we have this thing that makes sense now. We have these physical properties that make sense based off their intermolecular forces. So I'm going to stop now. You guys have about 30 minutes to finish your lab sheets with your drawings and your diagrams and the IMFs part. So the last column, you probably are now like, oh, that's what that means. The last column, both of those are going to be what you can fill out in today's minutes. I have a little bit more to tell you about some of these, but I'm going to wait on that because I've been having to work most of the hour now. So sorry about that. Same thing as last week. Paula, I'll come see you. Okay? Bring your little sheet with you. I have more of those. I think you did too. I saw you looking and I knew. So I found it. So go to lunch or until I come.
I'm not tutoring here too late in that, so I have to get my lunch.
Go get your lunch.
Yeah.